All right, so the lab that I just posted is going to be about the planet Pluto and how you measure the size of the planet Pluto. When Pluto was first discovered, it was just a dot in the sky. And so what they did was they tried to figure out as much as they could about it. But then they eventually discovered that it had a moon. Now, just a few years after the discovery of the moon, if you looked in the lectures, the moon was passing in front and behind Pluto. That gave them the first actual real way of measuring the size of Pluto. And so that's what this lab is going to be about. And so to do this, we need to know a couple things. We need to remember what we know about eclipses. So if you've got, for example, the moon passing with the sun, or in this case, Pluto's moon passing in front of Pluto. So if it's over here, it's moving in closer. So eventually, what's going to happen is that Pluto's moon reaches just on the edge of Pluto right there. Now, when that happens, then Pluto's moon Charon starts moving in front of Pluto, and then it starts dimming down the light. So instead of light of Pluto plus its moon, we're losing a little bit of Pluto's light because it's being blocked. And so what happens is, if you were making a graph here of the brightness, then at this point it's going to start getting dim because Pluto is there. So it's going to start getting dim. Okay. Eventually, the moon is completely in front of Pluto. So when that happens, it quits getting dim. It can't get any dimmer than that. And so as the moon moves across in front of Pluto, it stays roughly the same brightness. And then when it gets to the other side over here, it starts coming out from in front of Pluto. When it starts coming out from in front of Pluto, it starts getting bright again. And eventually, it is all the way out. And when it's all the way out, then it's constant brightness again. So if you made a graph of magnitude versus time, it would look something kind of like that. And so we call this time right here, when you first start covering it, that is T1. So that would be T1 right there. This is T2 right here, where it's completely covered. So that's going to be T2. And this is T3, where it starts to come out. So that would be T3. And then this is T4, where it is all the way out. So that's T4 right there. Okay. So that's the basic theory of this. And so what you're going to have is you're going to be given on your lab some data. And the data was taken at an observatory in Massachusetts. And so there's a little bit of random fluctuation in there. And so you're going to have a graph. And so you're going to set up your graph. And so when you set up your graph, you're going to have a y-axis and x-axis. I would encourage you to use graph paper or Excel or something like that to do this, rather than just freehanding it on a piece of paper. Put 0 up here. Now this is magnitudes. Magnitude, the bigger the magnitude, the dimmer it is. So dimmer, we want to go down. So that means this is going to be 0.05, 0.1, 0.15, 0.2, 0.25. So the number's getting bigger going down. So you can do that by hand on a graph paper or on Excel. Just click a button, say reverse the order of the axis. And then down here, this is time. So you can do this in 15-minute intervals. Okay, so every 15 minutes is one line over here. Okay, because the data is being given to you in 15-minute intervals. And so what you do is the data is going to be like this, and then now it's kind of random fluctuations here because the atmosphere was kind of disturbed a little bit, when they were making the data. So then what you want to do is figure out those times. Okay, so what I would do is I would say I have a graph there that looks kind of like that. And then at the top here, we know that's going to be flat, and it's going to be flat over here. And on the bottom, it's going to be flat right there. And so this should be kind of like a straight line there pretty much, and kind of a straight line there. It's not going to be exactly straight because of just random fluctuations. But what you do is this time right here, that time right there is T1. That time right there is T2. That time right there is T3. And this time right there, that's going to be T4. Okay, now, how do you get these times? What you do is you draw these straight lines on that graph. So it's not, don't connect the dots. That's not going to work for you. What you want to do is graph it and then draw straight lines where the straight lines intersect. You just go straight down. That's why you want to use a graph paper, because on the board here, these lines aren't really straight. They're kind of wiggly. Okay, so use a piece of graph paper, something that has vertical lines. Go straight down to read off those numbers. You know, these are 15-minute intervals, so read off the exact minute. Now, how does this help you? Remember, the time between here and here is the time between the moon being there to the moon being there. The time here to here is the time between the moon being there and the moon being there. So that means that this time and this time both correlate to the moon Charon, that's Pluto's moon, moving its own width. That means you can use that to figure out how big the moon is. The time from here to there, that's going to be from there to there, from T1 to T3, that's going to be the time from the moon here to the moon there. Or from T2 to T4, that time is going to be the time from there to there. Both of those correspond to the moon moving Pluto's width. So that way you get to move the entire width of Pluto. Okay, so how does that help? Well, we know that the moon is orbiting around like that, and so we happen to know the orbit size, and we happen to know the period, the time it takes to go around. That's going to be given to you. Well, you know the distance around a circle is 2 pi r. That's the circumference of a circle. Okay. And so 2 pi r, circumference of a circle, and so that means that as this thing goes around here, the speed is distance divided by time. Distance divided by time, that's speed. Now, if you know this time and that time, that's the moon moving its own width. Okay, so you take the average of those, and that time times the speed gives you the size of the moon. Speed times time is distance. For example, 50 miles an hour for 3 hours is going to be 150 miles. 50 miles an hour times 4 hours is 200 miles. And so speed times time is distance. So that would let you figure out the size of the moon. Now, if you know this time and that time between T1 and T3 or T2 and T4, that's going to be the width of Pluto. So if you know that time, that's the time it takes to go across Pluto times the speed, that's going to give you the size of Pluto. And so this is how you measure the size of Pluto and the size of Pluto's moon. So that's what this lab is about, is measuring Pluto and measuring Pluto's moon. And so you're using this graphical technique right here to do this. It was only possible to do this after they discovered that Pluto had a moon. And then once they did, then they started being able to do this sort of thing. And so with that, we were able to measure the size of Pluto, measure the size of Pluto's moon. Up until that point, we were just guessing at how big Pluto and his moon were. This allowed us to make the first measurements up until the New Horizons spacecraft got there up close, and now we can see up close how big it is. But this was how they did it until that point. And so this lab reproduces that for us.